What could we grow in Mars' regolith? Will telescopes ever be built in space? And whatever happened to space elevators? All this and more in this week's Overtime Question Show. Hey everybody, I hope you're enjoying your summer. I know I am. And this is the next episode of our Overtime Question Show. Now, normally we go on hiatus for our live streams during the summer, but we thought we would just delve back into our backlog of previously unseen question shows that we recorded on the channel, which we call Overtime. And so every week we're going to compile and edit up a nice collection of questions that were asked last year. So this is two shows that came out in September and October of 2023. All right, enjoy the questions.
Horizon Brave, surprise botany question. If we get back samples from Mars, could we plant Earth-based seedlings in it? Any nutrients would be totally different. So we haven't actually tried growing plants in Martian regolith because we've never retrieved samples from Mars. But we have tried growing plants in lunar regolith, and they sprouted and then they died because there's nothing in the regolith for them to eat. There's no organic material in the regolith. And so if you've ever planted seeds in just sand, then the seed pops out and then it dies because there's nothing for it to extract any additional resources from. And so we would assume that it would be the same thing on Mars, that when the Mars sample return mission comes home, somebody's going to try planting some plants in Mars regolith. And we can predict that the plant will pop out and then it'll die. And that's how that'll work. And so that was the whole point of the Martian. If you remember the Martian and he has to grow potatoes in the regolith, the first thing he did is go out to the toilet and grab everybody's poop so that he can grow the potatoes, because they need that organic material. They need the bacterial life in the soil to be able to supply the nutrients to the potatoes. And so we would need the same thing. And that's going to be one of the limiting factors. Like when we go to Mars and we try to start a farm on Mars, we're going to have to bring all of this organic material that we can get the whole process kickstarted. And until we've got that microbiome, the bacterial microbiome or the fungal biome to connect the plants, they're going to have a hard time surviving and for us to be able to thrive off of them. John E. When I watch the large telescopes on Mauna Kea, I often see a bright laser emitted from the scope. I think it's for adaptive optics, but what is it changing? Secondary sensor, etc. That is so cool. Obviously it makes sense, but if you're on the big island of Hawaii and you look up to the observatory, and if they're doing active observations with their adaptive optic system, they're going to be firing this big laser into space, and you would see that happen. I never thought that this was possible, but now that I think of it, of course it is. So what's happening with an adaptive optic system is that they're shining an artificial star into the sky. And what that does is that gives the astronomers, it gives the computer on the telescope a fixed position that it knows how bright this thing is supposed to be and what it's supposed to look like. It's supposed to be a dot in the sky that it can then go, okay, I should be seeing a dot. And then I don't see a dot. I see a distorted blur. So I'm going to change the shape of the mirror to adapt to the shape of the dot to bring it back into a dot. And so it actually deforms the mirror of the telescope. Sometimes it's the primary mirror, sometimes it's the secondary mirror of the telescope, but actually there's pistons underneath the back of this telescope and they deform. And so the pistons come up and down behind this mirror and they warp and change the shape of the mirror to adapt to the shape of this guide star that's put into space, or into the sky, into the atmosphere, until it resolves back into a dot the way they're expecting. And then they're able to, apply that. And the newer versions, like the big telescopes on Mauna Kea, they have one laser for the guide star, but the upcoming telescope, like the extremely large telescope, it has four. Looks like turbo lasers coming off of this telescope, because it's able to now have all four in the sky right around where it's observing. And then it's able to adapt so that the regions of the atmospheric differences are, is able to change around one star and then another star and another star, and try to keep as much of the field of view in perfect focus as possible. It's an amazing technology. And the fact that it does as well. I mean, it really allows astronomers to ignore the atmosphere. And so like one of the things that I don't know if it's like the dirty little secret, but for the longest time, right? Like we had telescopes here on Earth, big telescopes, like telescopes that were whatever, 1 meter across, 2 meters across. But a big telescope was actually not a lot more useful than a smaller telescope because of the atmosphere. There's just a limit to the dimness of an object that you can see because of the perturbations of the atmosphere. It was only with the development of adaptive optics in the like 80s that problem went away. And now there's no limit to how big a telescope you want to build on Earth and how clear an image that you can get. I mean, the extremely large telescope is going to be capable of observing Earth-sized worlds orbiting around sun-like stars from the surface of planet Earth, thanks to the power of adaptive optics and other instruments on board, like its coronagraph and things like that. But yeah, the fact that you can see the laser coming out of the observatories is really cool. I want to see that. Amir, why is there any ultra big modular space telescope that was assembled in space? There's no great reason, and I think that we are due for a space-based telescope to be assembled in space. There was a paper that I reported on like 5 years ago about the potential, like there is a proposal within NASA to build a space telescope in space, similar to the way they build the International Space Station. So when you think about it, right, like all of the parts of the International Space Station were launched to space, and then they were assembled in space. And so you got this giant machine that could not have been launched in any one single launch. And so the same thing could work with a space telescope. So you could launch, say, the hub of this, all of the intelligence and a couple little robot arms coming out the side of this main bus. And then it would fly up to the location where the space telescope is going to go. And then you send it its solar panels, and it grabs the solar panels and it bolts them onto itself. And then you send it the parts of the primary mirror, and it's able to assemble the primary mirror together and align everything together and build a telescope that could be any size in space. And, and this is an idea that is being considered by NASA. There are no specific plans. This brings technical risk back into the puzzle, having a space telescope build itself. And so like the Habitable Worlds Observatory is not going to use this. Probably, but I don't think there's a 100% chance that habitable worlds won't be assembled in space. I think there is a chance that it will be assembled in space because this proposal is making its way through NASA. I think it's one of the most exciting ideas in the future of space telescopes. And like we saw that it worked with the International Space Station. Let's see it happen with a space telescope of unlimited size. MC Hall, seems like JWST has been very successful. If it permanently broke tomorrow, would you say that we got our money's worth? If not, when? No. I'd say if it broke tomorrow, we would definitely not have gotten our money's worth. I mean, I think there are some intriguing mysteries that Webb is now starting to uncover about the formation of galaxies at the beginning of the universe, a lot of this other stuff, right? But it's not giving us the answers yet. It's sort of deepening the mystery. And so we need more data, and that's going to require more time. So I think by the end of that first 10 years of its original planned time frame, we will get some of those answers. But no, it would suck. Don't break, Webb, don't break. Jack Woods, have we heard any updates lately on carbon nanotubes and space elevators? Not really. There is a group of people who are continuing to meet. I think they're like the Liftport Society, who are continuing to meet and talk about space elevators. And at the same time, we're seeing the rise of 2-stage fully reusable rockets like Starship. And they're going to be price competitive to a potential space elevator with a lot of the downsides of a space elevator, like the limited cargo that you can carry on it and so on, right? Like a space elevator actually won't let you get very much cargo up compared to giant SpaceX rockets taking off. So, and we still don't have any material that you can build your space elevator out of beyond, carbon nanotubes are theoretically strong enough, or graphene. Anyway, but we can't make carbon nanotubes longer than a few centimeters long. So we're still not at a point where we can weave carbon nanotubes from here to geostationary orbit that would be required to make a space elevator. Everybody knew that chemical rockets were expensive, and it's ridiculous to throw your rocket in the garbage every time you launch it. It's madness. And so everybody was thinking about, well, like, what's a way that we could get off of Earth without having to put in the expense of chemical rockets? And there was a bunch of ideas, like electromagnetic launchers, like giant rail guns, or a tether, a space elevator. And theoretically it's going to work, but there's so many issues with a space elevator in terms of, like, how do you get electricity down the cable? How do you build the thing? How do you have materials and so on? And, like, those have just not been solved. Then you had the development of these 2-stage rocket systems like Starship. Like, in theory, and who knows whether this will actually be true, but Starship should drop the cost to getting into space by a couple of orders of magnitude. And so instead of it costing you, say, $3,000 per kilogram to send stuff to space on board a Falcon rocket, which is already one of the cheapest ways to do it. Like, instead of costing $10,000 per kilogram to go on the space shuttle, it's going to cost you $100 per kilogram on Starship and on a fully reusable rocket. So that's about the price. Like, people were sort of estimating the price of space elevators is around $100 a kilogram to take things to space. But, with a space elevator, it's really hard to provide electricity, to supply the electricity up the cable to be able to make the elevator rise and fall. You can only have elevators, and every elevator that you add, you're having to add even more electricity to the system. Like, do you have solar panels on top of the climber that's able to climb up? How long is that going to take you? Is it going to take you a couple of weeks to get up to the top of the elevator, while Starship would take a few hours to get you to geosynchronous orbit? So it's just like, I think space elevators came from a time when we couldn't imagine a more efficient way to get off of planet Earth at scale. And this was the thing that everybody wanted. It was like, we want to get off Earth at the largest possible scale. And now there are strategies to do that at scale. Launch as many rockets, you take as much cargo off planet Earth as you want for close to as cheap as the laws of physics will permit. And so I think that the market opportunity for a space elevator has disappeared. And so I think we're going to see less and less of this when it's going to be less economical, less cost competitive. Like, the only thing a space elevator is going to have going for it is that it's freaking cool, right? It's such a cool idea, but that's about it. Like, I know that sucks. Like, here I am pooping on sci-fi Christmas. Cuplex. Could we expect Breakthrough Starshot to become reality in the next 20 years? No, I don't think so. There are a lot of technologies required to make Breakthrough Starshot happen, right? You've got this laser that is more powerful than any laser that's ever been fired before. You've got a spaceship that is using a solar sail made of material that's never been used or developed before. And you've got a spacecraft that is capable of being carried as a payload that nothing of that size and capability has ever been developed before. And so you've got all of these gigantic technical challenges that lie ahead. None of them sound like they're insurmountable, but the progress that's going to solve these problems is taking a while. Like, it's like we're probably closing in on 10 years since Breakthrough Starshot was first proposed. What's been done so far? Some thinking, a couple of new solar sail projects have been developed and launched. Maybe lasers have been made more powerful in that time, like at the National Ignition Facility. So I think you'll know that Breakthrough Starshot is going to try and send a spacecraft to another star system after you see Breakthrough Starshot being used to explore the solar system, because it's the perfect spacecraft to do that, right? You send this tiny probe at Ceres, and you zap it with a little laser and off it goes at approaching, 10% the speed of light. It gets to Ceres in a few hours and sends a bunch of pictures from the surface. You could send out 1,000 of these to 1,000 different asteroids that we've never seen before and send pictures home. That would be really cool. Or go back to Neptune, or check out Triton, or check out the moons of Uranus, or go to Sedna, right? There's all these places that you would want to go in the solar system. Go out to the solar gravitational lens. The list goes on of places to explore. And that when we've matured this technology and we know how to use this and we're comfortable with the limitations of how much laser is required and how big a sail is needed, what is the communications protocol and so on, then we will have a much better understanding. But like, didn't that sound like a big to-do list that I just gave you? Like, we're looking at decades. Now, I'm going to be doing an interview with Marshall Eubanks, who's one of the people behind Project Starshot, in like 2 days. And so, he's looking at how do we get the communication signals back home, building a giant mesh network with these satellites. But, we'll definitely talk about sort of where we're at and what are the updates and what's the feasibility. So I'll give you an update then. An evolving ape. How big would a black hole be that is 1/100th the gravity of Earth, and how close can you get physically to it without being spaghettified? Now, I haven't done the math. Like, the black hole, the size of the Earth, would have an event horizon that's 1 centimeter across. And so it would be like a millimeter across, or like a fraction of a millimeter across. How close could you get without being spaghettified? Pretty close. I sort of think about, like, there would be tidal forces for sure. It would have the gravity of a small asteroid, and it would be a millimeter across. So I think you would experience tidal forces when it came in contact with you, but I'm not sure like how close you could get. A few meters away, and you would start to feel those tidal forces where it was starting to pull your body apart. It seems like I haven't done all the math. You'd be taking the gravity of a small asteroid like Vesta, but compacting it down into a millimeter. And so like you wouldn't experience a lot of gravity on the surface of Vesta. But if the Vesta was packed down into a millimeter across, it would be very intense if it got very close to you. Series K. Lee, could the Gemini North and Gemini South work together to do optical interferometry? No. Like optical interferometry, like think about the Event Horizon Telescope, right? That you've got these radio telescopes around the world that are working together to act like a telescope the size of planet Earth. It's a cool idea. And you wonder, like, could we do that with a optical interferometer? And the very large telescope is 4 large telescopes, and I think another 4 smaller telescopes that can work together in near infrared to work as an interferometer. But they have to do that using like interference of light on site. Like they know exactly how far away those telescopes are from each other. They are sending their data streams live to each other, and then they are sort of tuning the signals to turn it into one image. And that's only possible because everything is so precise and so careful on location. And to try and like add the light from the Gemini North and the Gemini South and have that be an interferometer the size of planet Earth, no, it wouldn't work. Like you're not going to be able to line up those 2 telescopes down to the 500 nanometers. But, in theory, you could have the 2 telescopes be additive. So you could have the Gemini North and the Gemini South both looking at the same object, and then you could mash their data together, and it would be the equivalent of a telescope that is the size of double either of those telescopes, but not the size of the distance between them. Like that's the magic of the interferometer. And so you could have a telescope that is the equivalent of 2 giant telescopes, but not an interferometer. We're probably not going to get a really powerful interferometer until somebody builds one in space. And LISA is going to be building a gravitational wave observatory, which is going to be kind of it's going to be using lasers as an interferometer to try and keep itself in balance. And so a lot of the technology of building an interferometer in space is going to be done with LISA. And so at some point we will have a space-based visible light interferometer where you have 2 spacecraft that are flying at some distance between, some far apart, and they will be able to have the resolution of a telescope that is the size of their distance. So you fly these 2 telescopes 500 kilometers apart, and you have a telescope that is 500 meters across. And that would be amazing. Duke N Channel, simple question. Thoughts on the moon Europa? What to expect in future missions? What is the most exciting thing about Europa for you? Yeah, like Europa is really cool because it is this moon of Jupiter that is, because of the tidal effects, we know that it has a liquid ocean underneath this thick ice shell. It probably has some kind of geological activity that is underneath the moon. Like right next door is Io, which is the most volcanically active place in the solar system. And so you can imagine that you're going to have a some level of volcanism at the bottom of Europa. And so that's going to be sending nutrients into the water. So you've got all of the stuff you need for life. You've got water, you've got nutrients, hydrogen gas, probably. And so all of this emphasis was placed on Mars with all the spacecraft and all the plans to explore Mars before people really realized how exciting Europa and Enceladus are. Like, Enceladus is even more exciting than Europa because you can go there and fly through the plumes that we know are there and detect and, search for the presence of some kind of biological activity in the plumes at Europa. So, or Enceladus. And if Europa has the plumes too, then that works too. And so NASA's Europa Clipper mission is going to be on its way to Europa. It's going to help figure out if there are plumes at Europa, and then hopefully try and sort of examine the area where the plumes are coming out and try and analyze the water that's coming out of those plumes and see if it has the presence of the kinds of chemicals that we see at Enceladus. Yeah, Europa is great. But at the same time, like, it sucks, right? Because it's like underneath this 100-kilometer thick ice shell. And like, how do you explore that? And how do you search for life down there? And what does life even really mean in such an alien place? And then at the same time, if we do find life, then boom, we've got this second place in the universe where life formed. And if we're not related in any way, then it formed completely independently. And if that happened, then it's game on, right? Then it means that there's life everywhere. There's no question. Like, if we find life on Europa and it is utterly unrelated to us on Earth, we have nothing in common. Like, it doesn't use DNA, uses some completely different thing. We have no common ancestor. Then it really means that life has got to be everywhere across the universe. And then, of course, you wonder, where is it? So, just like finding some place anywhere, ever, that has life would just give us this answer about whether or not we're alone in the universe. And Europa is the closest place. Avo third. If the universe is expanding, is it all moving away from the origins, and are all the galaxies moving at the same speed? If so, how do galaxies collide? So at the largest scales, the universe is expanding, or the universe is becoming less dense over time. And so when you look in all directions, every galaxy that you can see is moving away from us, except for a couple that are relatively close, that our gravitational sort of attraction to that galaxy is stronger than the rate that it's moving away from us. And there's not a lot, like Andromeda, M33, Triangulum Galaxy, a couple of like other dwarf galaxies in the local group, and everything else is moving away from us. Now, there's not like one point that galaxies are moving away from. Like, all galaxies are moving away from all of the others. And so you can have galaxies collide if in some small local area their gravity is pulling themselves together, but beyond that, everything is moving away from everything else. Music 100 vid. To get a multi-star coronagraph, could we layer a programmable LCD screen on a sensor CCD so that the starlight from all the stars will be blocked, letting only the light from the planets? So I asked almost this exact question to somebody. I did a whole interview about coronagraphs. So I talked to the woman who is working on the Nancy Grace Roman coronagraph, which is sort of like a prototype for the coronagraph that's going to go with the Habitable Worlds Observatory. And I asked a version of that question, and I think the answer that I got was no, that for right now, for a coronagraph to work, you can only really block the light from one specific star, that you're essentially sacrificing all of the rest of the detector to focus on the light that's coming from this one star. And so you have a very narrow field of view. And normally the Nancy Grace Roman has this enormous field of view, but you're sort of using all that field of view, you're discarding it, and you're just focusing on one little part, and then you're jamming a lot of information into the detector. I'm sort of summarizing this really badly because I still sort of barely understand it. But the way the trade-offs work is if you want to have this really powerful coronagraph. And so her number was, you can have a planet that is 1/300 millionth the light of the star. What that gets you is Jupiter. So the coronagraph that's on board the Nancy Grace Roman telescope should theoretically be able to observe a Jupiter-sized planet orbiting around a sun-like star, which obviously doesn't give us the Earth that we want. Like, that's what the Habitable Worlds Observatory is going to do. And maybe they can do it just with the raw coronagraph alone, or maybe they're going to be able to pull it off with with a star shield. But the idea that I like, and this is where you're getting at too, right? Is that imagine you could do like a Kepler style mission where you take your telescope and it's got some kind of electronic coronagraph that is trying to block all the light from all the stars in the field of view. And then you just stare at this one field of view for days, months, weeks, years, and piece out planetary observations. And I don't think we're there yet. Like, I don't think this technology exists. But there is like next generation stuff, like quantum telescopes, where maybe you could have, like there's this idea of quantum nulling. So if you have two telescopes that are separated and are able to see a star from two different perspectives, like even if it's like 100 meters away from each other, then you can take the wave fronts of these stars as they're moving into the detectors, and then you can interfere them together and you can disappear the light from the star, and you're left with the planet, which you're seeing at a different angle. I'm not exactly sure how this works. Again, sort of, I'm still learning about this stuff, and so it's still sort of very fresh in my brain. It's very complicated, but there are new and interesting technologies that are coming out for coronagraphs. There are other methodologies, said like there's like the nulling, there's the onboard coronagraph, there's the star shield, and there are like this one more order of magnitude is going to be required to get out of coronagraphs to reach the Earth-sized world around a sun-like star, which is what the Habitable Worlds Observatory is going to try and achieve. So when Nancy Grace Roman launches, and I hope when you hear this interview, you'd be like, okay, now I get it, right? Like, it's going to help characterize dark matter, dark energy, help figure out the large structure of the universe, but it's going to have this prototype coronagraph that is going to pave the way for the Habitable Worlds Observatory. And so we're going to watch the results from this coronagraph very carefully. Christopher Smith, could you please explain how light travels further than 13.8 billion light years due to the expansion of the universe? Just that the things, like from the light's perspective, it's traveled from, for 13.8 billion years. But over this time, the expansion of the universe has been carrying the thing that the light emanated from us away from each other, and has literally just expanded the space in between. And so this has caused the light's wavelengths to stretch out as it's trying to cross this gap. I don't know, kind of like imagine like a slinky. You start the slinky from one place and you start to move it towards a destination, but then the place you started is moving away, and then the destination is moving away. And so you're having to sort of stretch the slinky to be able to connect these two things together. And so, if you could just like stop the universe right now and then fly to the place where the light was being released for the cosmic microwave background radiation, even though that light has only been traveling for 13.8 billion years, that location is 46 billion light years away from us. Of course, if you actually could do that and you went there right now today, it wouldn't look anything like the cosmic microwave background. It would look like us here today. It would look like a regular galaxy because, we're seeing it back in time. Like, not actually us here today. Like, you wouldn't see a guy doing YouTube in that distant galaxy. Busy Billy B33. In our search for extraterrestrial life, do astronomers look for signs of machine life, worlds that are colonized by self-replicating machines sent out by intelligent beings? Sort of. So like, we can't see anything that isn't really close to us. And so for us to be able to see things that are very far away, they're going to have to be very dramatic sorts of things. And so for an example would be a Dyson swarm, right? Like if an intelligent civilization was trying to use up all of the energy coming from the star, they would surround the star with satellites that would harvest all of the energy, and those satellites would release heat because you have to, or you make an oven. And so we would see that a very weird star, it looked like a star, but it was giving off infrared in a way that just doesn't make sense. And we could even see partly built ones. So we could see a half-built Dyson swarm where some visible light is coming out, but then sometimes it's infrared. And then you could take that idea to the next level. You could say, well, what if a advanced civilization is sort of moving outward at the speed of light and colonizing stars and turning them into Dyson swarms? And you would see this sphere in the sky that had a whole bunch of stars that were infrared. And you'd be like, okay, that's coming our way. That's interesting. And then you can imagine like even a more advanced version where a really advanced civilization is starting to rearrange the stars and their entire galaxy into a form that makes more sense. Like just a straight up galaxy is inefficient. We could do better. If you sat down and imagined what is the best possible configuration of a galaxy, it wouldn't be a galaxy. It wouldn't be a galaxy filled with stars and star formation, all that. It would be some kind of sphere of red dwarfs, each of which was surrounded by a Dyson swarm, and they would be in these perfect orbits that were getting close enough so that you could travel from star to star, but you wouldn't be interacting. Like, there wouldn't be any stray black holes and material around to bonk into your Dyson swarms. So there is a perfect galaxy that you can imagine. And so that's the kind of thing that if we were looking for out there in the universe, an obvious example that there's an intelligent civilization that's in the process of gobbling up space, that's what it would look like. And yeah, we would absolutely see that. Now, we wouldn't know whether it was machines or, people or alien creatures that were just really organized and intelligent, working hard. But I think that's the kind of thing you would expect to see.
I'm going to talk about what I think is the best science fiction book ever written. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Monzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Cheplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. People always ask me what is my favorite science fiction book. And I don't like superlatives. I like a lot of books. I like the Foundation series. I like the Revelation Space series. I like the Culture series. But if I had to be pinned down, like what is one of the best science fiction books ever written, it is A Fire Upon the Deep by Vernor Vinge. And it is really hard to encapsulate what this book is about, but kind of imagine the Milky Way, where the farther you are away from the center of the galaxy, the more your technology is able to advance. And so you've got the slow zone at the center of the galaxy. And then as you go farther out, more complicated technological civilizations can arise. And in one of these areas, there's this sort of area where all of the sum knowledge of the universe is combined, and a rogue artificial intelligence sort of wakes up and starts to go on a rampage, and the various forces in the galaxy have to figure out what they're going to do about this. And sort of it's at this giant kind of cosmic level, but also the book is very specifically about this world where sort of a race of creatures are at like a medieval level, but they're like a hive mind, and they're trying to sort of win a war against each other. And this sort of plays into the larger narrative as well. It's like I said, it is really hard to explain this, but there are so many amazing ideas, so many great stories that go through this one book that, if you read it and if you're into this kind of thing, it's going to blow your mind. And it's kind of sad because Vernor Vinge passed away earlier this year. And so he's given us a lot of great books. He was the guy who came up with the concept of the technological singularity. And so, it's too bad that we won't get any more books from him, but the books that we do have are absolutely fantastic. All right. We'll see you next week.